An underappreciated aspect of plant immunity is that unlike animals, plants do not have an adaptive immune system, which means that plants rely solely on their innate immune system to defend against various pathogens. Not only plant readiness to respond to multiple pathogens is important, but the speed with which they respond to these pathogens is significant to determine resistance or susceptible outcomes. Plants achieve this speed by precise coordination of intracellular trafficking and using the cytoskeleton made up of actin and microtubules as highways, which they use to transport antimicrobial cargo to the site of pathogen attack. However, the logistical decision of which highway, whether the actin highway or the microtubule highway to be taken, is not known, and whether this determines the specificity of the cargo delivered is also not known. A good analogy for this would be, imagine if there are multiple highways leading into a city. The decision of which highway to take to get into the city would depend on a lot of different factors, and we do not know these factors. We recently identified TGNap1 in the model plant Arabidopsis as a protein that connects the trans-Golgi network vesicles with the microtubule cytoskeleton, thereby acting as a cytoskeleton organelle bridging protein. By linking the TGN vesicles with the microtubule cytoskeleton, TGNap1 enables either faster or directional transport of vesicles to their final destination. Now, during pathogen attack, there is an increase in secretion and multiple pathways are recruited to ensure that vesicles carrying antimicrobial proteins are moved to their eventual destination. One of the proteins recruited in this role is TGNap1, and it's recruited to transport vesicles carrying antimicrobial proteins using the microtubule cytoskeleton. Plants lacking TGNap1 are more susceptible to pathogens, as the delivery of the antimicrobial proteins to the site of pathogen attack is either reduced in the absence of TNAP1 or completely lacking. TNAP1, in addition to its function, also operates in a pathway that is independent of the canonical salicylic acid dependent pathway, thereby revealing another level of networking which is beyond canonical hormonal defense pathways. However, antimicrobial proteins are still found at the site of pathogen attack, although found at a very low quantity, thus indicating that there are multiple pathways that are recruited for defense. Now, coming back to our original analogy of multiple highways leading into a city, the loss of TNAP1 would be comparable to a specific highway being blocked, therefore causing traffic jams, but there is still traffic moving into the city at a much slower pace. A surprising avenue in our discovery of TGNap1 as a cytoskeleton organelle bridging protein was also discovering the heterogeneity of the TGN vesicles, which was not known before. We found that a single TGN vesicle carrying antimicrobial proteins can harbor 2 or more cytoskeleton organelle bridging proteins, which in theory would allow the vesicle to be transported either via the actin cytoskeleton or the microtubule cytoskeleton, thus making TGN not only a hub for protein or cargo sorting, but also a convergence point for the actin and the microtubule cytoskeleton. Now, whether the TGN vesicles flip between actin or microtubule is not known, or whether they move on either the actin cytoskeleton and at some point move to the microtubule cytoskeleton or vice versa is also not known. Evolutionarily, it would make sense to retain the ability to move on both actin and the microtubule cytoskeleton, as this would allow the vesicles to have a backup in case pathogens attack one particular cytoskeleton component, either actin or microtubule, allowing the vesicles to move on the intact cytoskeleton highway.